Hello everyone, I'm here to present our new ICML 2024 work, LayerMerge Neural Network Depth Compression through Layer Pruning and Merging. The authors are me by myself, Jinwoo Kim from Seoul National University, Mara Al-Halabi from Samsung SAIT AI Lab, Montreal, Mingi Ji from Google, and Hyunho Song from Seoul National University. The problem we are focusing on is depth compression in convolution neural networks. What we're trying to do here is we try to reduce the depth of the CNN to make it more efficient in the inference time and speed up the inference latency. Existing methods in reducing depth of the CNN usually follows one of two approaches. First, they either try to prune the convolution layers by selecting less important convolution layers, or they try to prune activation layers, then merge resulting consecutive convolution layers into a single convolution layer. Pruning convolution layers has its own limitations in that they aggressively remove parameters. Thereby, there are some risk of losing important information in the network. Pruning activation layers and merging consecutive convolution layers, they have their limitations in that the kernel size of the merged layer increases as layers are merged, thereby negating the speedup gains. To illustrate, if you're merging two 3x3 convolution layers, it will result in a single 5x5 convolution layer. But if we are merging three 3x3 convolution layers, it will result in 7x7 convolution layer. Thus, it undermines the latency reduction when we merge layers in CNN. To this end, we propose LayerMerge, which jointly prunes convolution and activation layers and merge resulting consecutive convolution layers at the test time. Therefore, we have the best of both worlds. To show you some qualitative example, the figure above denotes the method that prunes activation layer and merging consecutive convolution layers at the test time. This results in enlarged kernel size by having 7x7 convolution layer as the merged layer. Our method, on the other hand, we jointly prune convolution and activation layers, thus bypass this kernel enlargement problem, thereby having 1x1 convolution layers as merged layers. Thus, we find more efficient network structure in the end. To write this down more formally, we optimize two sets of layer indices, where A denotes where we keep the original activation layers and C denotes where we keep the original convolution layers. Then we maximize over two sets where the objective is the performance of the pruned network, where the constraint is the latency of the merged network. Note that this merging process from pruned network to the merged network keeps the network output unchanged because we're merging only the consecutive convolution layers without the activation layers in between. So here, the challenge of this optimization problem is that it is NP hard, involving exponential search space. Therefore, we propose a surrogate optimization problem, which can have a tractable optimization solution. So instead of optimizing the objective, the performance of the pruned network, we propose to optimize surrogate objective, which is the sum of importance values of merged layers. And for the constraint, instead of the latency of the overall merged network, we estimate this value as the sum of latency values of merged layers itself. Here, the importance of the merged layers, we define it depending on the change in performance after replacing the corresponding part of the original network with the merged layer. So if the performance drops less, then we assign higher importance value, and if the performance drops more, then we assign lower importance value. When we construct the lookup tables for these importance and latency values for each merged layer, there's one key observation that we exploit. So suppose that we're merging from I+1th layer to the jth convolution layer. Then the choice of C only affects the latency of the merged layer via the kernel size K. So based on this observation, we propose to construct lookup tables with entries I, j, k, where this entry denotes from the merge layer from merging I+1th convolution layer to the jth convolution layer with having kernel size K. If multiple choice of C results in the same merge kernel size K, then we choose the combination of C with the largest L1 norm. So to wrap up, the surrogate optimization problem can be written as follows, where we maximize the sum of importance under the constraint of sum of latency. This surrogate optimization problem can be solved exactly using dynamic programming algorithm in polynomial time. The dynamic programming recurrence can be is written as follows, where if we define the maximum objective over the first L layers with latency budget T, then we can compute the optimal solution by recurrently computing for the intermediate layers. Optimal objective for the intermediate layers. We evaluate our method upon two tasks, image classification tasks and image generation tasks. For classification tasks, we evaluate on ImageNet dataset and ResNet 34 architecture and MobileNet v2, two types of MobileNet v2 architecture. For image generation task, we evaluate on Cypher 10 dataset with DDPM network. Layer only method denotes our layer pruning variant of our method, which involves knapsack algorithm, which is very analogous to our method, LayerMerge. But it only prunes the convolution layers instead of jointly pruning both convolution and activation layers. So experimental results show that our method outperforms the depth reducing baselines in convolutional neural networks, both in classification tasks and image generation tasks, having a more efficient network. These are some qualitative results of applying LayerMerge to pre-trained MobileNet v2 architecture and DDPM architecture. And as you can see, even with massive speed up, you can see that the prediction output stays fairly consistent. And for DDPM architecture, even after the compression, the generation result stays fairly consistent. In conclusion, LayerMerge reduces the depth of CNN by jointly pruning convolution and activation layers to make network more efficient while maintaining performance. The results show that LayerMerge outperforms current methods for reducing network depth in tasks including image classification and generation. You can see more detailed results and explanation in this GitHub repository where we open source all the codes that we used in our paper. Thank you for listening, and if you're interested, feel free to visit our poster session or contact me personally. Thank you for listening.